Okay, so chapter 5. Creating a relay logic diagram, or an RLD. Okay. Objectives in this chapter are pretty straightforward. This slideshow is only like 11 slides long, including the title page. So there's a whopping 10 slides worth of information here. But our objectives are going to be to use symbols to represent different types of input and output devices. Going to create relay logic diagrams using standard relay logic rules, which we're going to explain here in a little bit. Create relay logic circuits for process and industrial control problems, which is what the lab is. Okay, sometimes relay logic diagrams are called elementary diagram, line diagram, or relay ladder logic. From here on out, we will use the term relay logic diagram, or RLD, to describe the ladder logic diagram. The reason why we do this is because it is the first step in creating a program for PLC. You have to know how the machine is going to function before you can write the logic to control it. And they show symbols for the input and output devices. After the relay logic diagram is drawn, convert a PLC ladder logic, often called a ladder diagram, LLD, ladder logic diagram, as opposed to RLD, relay logic diagram. Ladder diagram is used to program the PLC, and the program defines the operations performed by the PLC. This particular graphic, the way you read it, you have your power rails, okay, labeled L1, L2 because this is from SLIC 500 days. More than likely nowadays it's going to be 24 volts and 0 volts. Okay. But you have a switch, push button, limit switch, and motor starter. In order to get this motor starter to operate, we have to have a continuous path of current to flow from L1 to L2 through this load. Okay? So switch 1 has to be closed, push button 1 has to be depressed, and then switch 1 also has to be closed in order to get the motor starter to turn on. Okay? Any brakes like that, any one of those open up, motor stops. Okay? Voltage between two rails labeled L1 and L2, plus 24 volt DC, 0 volt, 12 volt, 0 volt, whatever voltage is your system's running at. These days it's almost assuredly going to be 24 volt DC. About 99% of all control systems are 24 volts nowadays. The reason why it's 24 volts is because it's considered a safe voltage. As long as you're not licking the shiny bits, it won't hurt you. It'll get your attention, but it won't hurt you. Okay? Each row in a relay logic diagram is called a rung. It's often referred to as a ladder diagram because those are the power rails that look like stiles on a ladder. And then the individual rungs Makes it look like the steps on a ladder. Okay. Relay ladder diagram can have more than one row. Really good chance it's going to have more than one. Vertical lines that connect the rungs are called rails. More accurately, power rails. Okay. Relay coils and contacts, we'll use a control relay, that's what the CR is. Being used to control solenoid in this case. Relay logic circuit can have several relay coils and contacts. So, the way this one's going to work, have a power rail. Okay, we have an open circuit here, so no current flow. Open circuit here, so no current flow. Open circuit here, so no current flow. Okay. Press the start push button, or sorry, PB1, which I'm assuming is start. And now power can flow through PB1, through LS1, energize the CR. Okay, you with me so far? When CR energizes, it's going to close this contact, it's going to close this contact. Okay. Now I can let go of the push button because I have a path of current flow this way through limit switch there and through to the solenoid. Okay. To stop this system, all I gotta do is open LS1. CR de-energizes, which opens that contact, as long as I'm not pressing the push button when limit switch 1 closes again, it doesn't do anything because I've got open here, open here. Okay. Did I lose anybody? Lane, you look like you have a rather quizzical look on your face.
So what's CR stand for?
Control relay. Okay. Rules for drawing relay logic diagrams. There are 9 rules that are accepted as standard in the control industry. I said earlier, creating a relay diagram is the first step in programming PLC. You have to know how the machine is supposed to operate before you can program it to operate that way. Okay. Rule number 1, input devices are placed near the lift into the rung. Rule number 2, one and only one output is placed on the right side of the rung. Okay. So, something like that. That's legit. That is not. You only have one output per rung. If you need to do this, put them in parallel. Okay. And you can put as many parallel branches as you want. Okay. Rule 3, input devices can be connected in series, parallel, or a combination thereof. So, series, These two are in series, these two are in parallel, and the combination of three is the combination. Okay. Rule number 4, output devices cannot be connected in series. So, as I displayed earlier, or demonstrated earlier, they cannot be in series, they have to be in parallel like that. Rule number 5, while input devices can be represented multiple times, in the relay logic diagram, each output device can only be represented once. So if you have multiple things that can control motor number 1, you can only have one motor number 1. You can't have one on you cannot do that. Okay. This can be, that works. That does not. Okay. All input and output devices must be placed horizontally, which means that is not legal. Okay. That is not legal. They all have to be placed horizontally. Okay. Current in the relay logic diagram must flow from left to right, so from positive to negative. That being said, when you're talking about a relay logic diagram, whenever you're using good old-fashioned relays and physical switches and stuff to do the control of your machine, electricity doesn't care, it's going to flow everywhere it can. So you can have a situation where it would flow in as long as I can find a path for current flow in a relay diagram, that's going to energize. So if I go through push button 1 and whatever this contact is and whatever this contact is, I'm still going to energize this coil. Okay, and I went backwards. So forward there, down this way, backwards through that one, down, forward through that one, and then to my load. Relay, you can get away with that. In ladder logic, i.e. PLC, it will not evaluate that is true. It always scans top to bottom from left to right. If it has to turn around and go backwards, completely ignore it. Okay. Rule number 8, diagrams must be numbered and commented correctly. Rung numbers are placed on the left side of each rung. So that's number 1, that's number 2. Okay. Instructions and symbols are placed, instruction symbols and comments are placed above the instruction. So this is PV1, this is PV2. They is LS1. That is not where that goes. Okay. Bad juju, that's bad juju. It should be up there. That's bad juju. Okay, that makes sense. Rung comments are placed on the right-hand side of each rung. So if this is motor one, start, let's fix this. Motor two, you know, if this is, you always want your descriptor to be something meaningful. Like this is, motor pump one, and this is the agitator that's in the tank that's, you're mixing stuff up in there so you pump it out with pump one. Okay. So you always want to make sure that that is something meaningful. You know, motor one, motor two, that's great, but what's it do? Okay. And then the location of each contact associated with the coil can be recorded by the right-hand rail near the coil. Replace can with should. Okay. Should be recorded. So let's say that this is M1, and that's M2. Get rid of some of this extraneous stuff. Let's see better what's going on here. Okay. We'll make that normally closed. Okay, so I have a normally open contact operate off of coil M1 on rung number 2. So over here, I'm going to move this up. And let me say, put a 2 there. Okay. That tells me that somewhere on rung 2, I've got a contact that's operated off of coil M1. I also have it normally closed on rung 2. I'm going to put a comma there, 2. I'm going to underline it to signify that it is normally closed contact. Okay. This one, I have one normally open contact on rung number 2, and that's the only one for rung or for M2, right? Okay, everybody get that? Technically speaking, you should also note below here that tells you which rung the coil is that operates that contact. Okay, so it's kind of a cross-reference. You can either go here and say, okay, I know my coil is gonna be on rung 2, or you can go here and say, hey, I have a normally open contact somewhere on rung 2, and then makes it easier to find. Okay, if your diagram is, 500 rungs long, and motor 1 control is up here on rung 1, and you got a contact that's associated with it down on rung 327, being able to reference it and, okay, well, I can skip 2 through 326 and not even look at them. You can imagine how much time that saves, right? Okay, so steps for creating. Have to clearly define the control problem. That's what the lab sheet tells you. It gives you the step-by-step narrative on how the machine is supposed to function. 2, review and follow discuss the problem, and then review and follow the 9 relay logic diagram rules, and then draw the logic. Okay. Any questions? You guys are all going to ace this, right? Good luck with that, huh? Here. Okay, let's do this first one together. So you guys can get a feel for what's going on here. Okay. So, number 1 says when switch number 1 is closed, green fire light turns on. That seems pretty straightforward, doesn't it? And 24-volt power rail. Zero-volt power rail. Switch number 1 is closed, green pilot. Okay. First of all, what is the schematic symbol for a switch? Something like that. Okay. That's switch 1. What's the schematic symbol for a green pilot?
The circle with 4 lines diagonally out with the G in the middle.
The rays. The G in the middle. Okay. Number 2, when switch 2 is closed, the red pilot comes on. Okay. Let's run 1, run 2. Okay. Next one, when both switch 1 and switch 2 are closed, only the white turns on. So Will that work? Why not?
Would you be input multiple times, like the same input on different ROM?
Well, nothing wrong with that. You can't have more than one output.
So you could have like switch one here, switch one here, switch one here. Okay.
Yeah, you can have input as many times as you want. You can only have one output.
Would it be that it would still turn on green and red? Probably.
Yeah. I close switch 1 and switch 2, this and that is the same switch. They're physically connected together. So if I close this one, I'm also going to close this one. If I close this one, I'm also going to close this one. Going to turn the green light on. But this says that when they're both closed, I can only turn on the white one, which means I have to turn off the red and the green. Right? Okay, so I need something to fix that. Since we're drawing a relay ladder diagram, I'm going to propose that we use a relay to fix it. So, anybody have a thought on how we can use the relay, where to put it, and that sort of thing?
I'm thinking like under the G, you put a M1, and under the R, you put a M2, and then you put 2 relays in front of the white. Is that just redundant too much?
We're not, M1 would suggest motor. We want you to do CR, we want you to do a control relay,
Okay.
okay? So, let's, there we go. Like that?
Yeah.
Okay, and where am I putting the contacts?
Now, instead of the switches, put them both in front of the white.
Okay. Series, parallel.
Series.
Okay. Does that fix it?
I think it still keeps the green and red on.
That keeps green red on. Close the switch. Green, you're going to receive power and CR1. You're going to turn the green light on and close that contact. Push switch 2. Red light's going to come on, energize CR2, and close that contact. But do both of them, green and red both turn on, both CR1 and CR2 energize. Close these 2 contacts, white turns on, but it's still got red and green. So that's not the right solution. Anybody else have any thoughts? Kind of thought about it. Any thought better? There's actually a couple ways you can do it. Simplest way is always the best way, right? Simplest way, the logic is a lot easier to follow. Fewer components equals less investment, less time to wire it up, all that kind of stuff. So What did something like that? Can you follow that? Normally closed contact. Okay. Press switch 1 if CR1 is not energized, green light turns on. Close switch 2 if CR1 is not energized, red light turns on. So I should label things properly. I close switch 1 and switch 2. My white light's going to turn on. It's also going to energize CR1 at the same time because they're parallel. Opens that contact, which turns off the green light. Opens that contact, which turns off the red light. You see how that works? Okay. See what you can do with 2 and 3.